Welcome to the lesson on section 5.4, Indefinite Integrals and the Net Change Theorem. In this lesson, you'll learn about the difference between a definite integral and an indefinite integral, the meaning of the definite integral as a net change, and how to use integrals to calculate displacement or distance traveled by a body in motion. A definite integral has limits of integration. In this example, the numbers above and below the integral sign are the limits of integration. Because of the limits of integration, the result of a definite integral will be a numerical value. In the absence of limits of integration, the integral is considered to be indefinite. The result of an indefinite integral will be a function. These are rules for integrating some basic functions. Because these are indefinite integrals, we have to add a constant at the end to give a formula for all antiderivatives of the given function. Take a look at the first formula. The integral of a constant k is k times x plus c. Notice that if we took the derivative of kx plus c, we would get k. The next formula reverses the power rule. The power rule for derivatives says that we multiply by the exponent and then decrease that exponent by 1. To take those steps backwards, we would first increase the exponent by 1 and then divide by the exponent. As an example, to find the integral of 4x to the 5th, increase the exponent to 6 and then divide by 6. That gives us 4x to the 6th over 6 plus c. Taking the derivative of 4x to the 6th over 6, we would multiply by 6, which cancels the 6 in the denominator, and then decrease the exponent to 5, giving us 4x to the 5th. In the next formula, the integral of sine is negative cosine because the derivative of cosine is negative sine. And in the last formula, the integral of cosine is sine because the derivative of sine is cosine. Just as the act of finding the derivative is to differentiate, the act of finding the integral is to integrate. Also, similar to working with derivatives, sometimes you'll find it useful to simplify an expression before integrating. To integrate x squared plus 5 squared, I would simplify first to get the integral of x to the 4th plus 10x squared plus 25. Using the power rule and the constant rule for integrals, I get x to the 5th over 5 plus 10x to the 3rd over 3 plus 25x plus c. In the second example, I would rewrite the square root of x in the denominator as x to the negative 1/2 first, and then use the power rule for integrals, increasing the exponent by 1 and then dividing by it, giving me 4x to the 1/2 plus c. Now we'll look at the integral as a net change. The net change theorem says that the integral of a rate of change is equal to the net change of its derivatives. This statement may appear to differ only slightly or not at all from part 2 of the fundamental theorem of calculus. The main difference is that we're looking at the integrand, which is capital F prime of x, as a rate of change. This statement has implications on our work with velocity and acceleration because they are rates of change. For example, by the net change theorem, the integral from a to b of velocity would equal the difference between its antiderivatives at a and b, or the positions at a and b, otherwise known as the object's displacement. The integral of acceleration would equal the net change between two velocities. In example 3, we're asked to find the displacement and distance traveled by a particle with velocity t squared minus 5t plus 4. On the last side, we saw from the net change theorem that the displacement of the particle will be the integral of the velocity. The integral of this velocity is t to the 3rd over 3 minus 5t squared over 2 plus 4t. Evaluating at 6 gives me 216 over 3 minus 5 times 18 plus 24. And evaluating at t equals 0 gives me 0. Simplifying, I find that the distance traveled by the particle is 6 meters. So the particle is 6 units to the right of where it started. To find the distance traveled by the same particle, I'll first need to determine the times at which the particle changes direction. Factoring the velocity, I find that the velocity is 0 at 4 seconds and 1 second. These are my critical values. Using my knowledge of the graph of the velocity, I know that the velocity will be positive to the left of 1 and to the right of 4, and negative between 1 and 4. If I simply found the integral of the velocity from 0 to 6, the area between 1 and 4 would evaluate as a negative. To make sure the backwards displacement contributes positively to the distance traveled, I'll subtract that part of the area. So to find the distance traveled, I add the displacement from t equals 0 to 1, subtract the displacement from t equals 1 to 4, and add the displacement from t equals 4 to t equals 6. From the beginning of this example, when we were finding displacement, we found an antiderivative of the velocity to be t to the third over 3 minus 5t squared over 2 plus 4t. Apply the net change theorem to each of these integrals and evaluate. The distance traveled will be 15 meters. Now that we know some rules of integration, we can revisit part 1 of the fundamental theorem of calculus. Let's consider the derivative of the integral from a to x of the function 3t squared plus 8t. Instead of applying the fundamental theorem, let's actually take the integral and then the derivative and see if we get the same result. Integrating 3t squared plus 8t, we get t cubed plus 4t squared, which must be evaluated from a to x. Evaluating at x results in x cubed plus 4x squared, and evaluating at a gives a cubed plus 4a squared. Taking the derivative, we get 3x squared plus 8x. The terms containing a drop out because a is a constant. This explains why it doesn't matter what the value of that constant is. All terms involving the constant will drop out when you take the derivative. If we had applied the fundamental theorem to find this derivative, we would have substituted x's for t's in the function 3t squared plus 8t to get 3x squared plus 8x, the same result. Now let's look at an example that would have required use of the chain rule. I'll just change the previous example so that the upper limit of integration is x squared instead of x. Again, I'll take the integral and evaluate it at both x squared and a. Taking the derivative will again make all terms involving the constant drop out. I need to use the chain rule to take the derivative of x squared to the third and 4 times x squared. If I factor the derivative of x squared from both expressions, I can see that my result is the same as substituting an x squared in place of the t's and multiplying by the derivative of x squared, which is what the fundamental theorem states we can do. This concludes our lesson on section 5.4, indefinite integrals and net change.